Hi, in this video, we're going to look a bit more closely at what makes a generator different and how that impacts our decision on when to use a generator. And in this case, we are going to compare generator to a function. The two look remarkably similar, and in terms of broadly in two areas. One is when a generator and when a function is actually executed and do actual real work, and also in terms of the amount of memory that they use. And as an example, we're going to return to our favorite Fibonacci numbers. On the left here is a function, fiblist, that returns a list of Fibonacci numbers up to the value specified by the n parameter here. On the right, it is a fibgen. It's a generator that yields all the Fibonacci numbers up to, again, the value that is specified in the n parameter here. And if you look at the actual code for either one, the fib list, obviously it starts with an empty list, and then every time it computes a new Fibonacci number, it appends that number into the list, and at the end it returns the list of all the Fibonacci numbers. And in the generator, as it goes through each of the Fibonacci number, it yields each one of them. Okay, but otherwise, yeah, they are very similar in code. And what we're going to look at first is what is the type of fib list itself and fibgen itself, right? Without actually calling them. And then secondly, then we will look at, when we invoke a function with an actual parameter, and then when we invoke a generator with an actual parameter, what is the type of data that it returns? And I've typed out the code here. You really should try it yourself. I'm going to run it, and we're going to look at the difference in the console output. And I actually copy it back into slides here, so it's a little easier to see the side-by-side comparison. So the first thing we notice here, fiblist itself and fibgen itself, they are both functions. Okay, even though we say this is a fibgen, but without executing it, Python sees the fibgen as a function. What's different is when we actually invoke or call these functions. Now, in this case, when we call fiblist with a parameter 100 here, now we know what it does, right? It runs and it returns a list. So the type built-in function here is going to give us the type of what this function invocation returns, which is, it's a list, right? However, for the fibgen, which is a function but has the yield keyword in it, that what it returns is not the list or any number just yet, right? But what it returns in that case is that it's a generator. So what this generator is, then it represents the work that it will do, but it hasn't done any work yet when we call it. So that is very important to keep in mind. So now that we have a generator, we want to be able to actually run it, right? So the most common way to run a generator, as we saw earlier, is just use a for loop on it, which will is the nice synthetic sugar that would just get all the results from a generator. But let's use the other way, which is to call the next on a generator so that we can see step by step what happens when we run a generator. And to gain some insight into it, I actually modified the fibgen slightly to print a few messages out. So, as we step through it in the slide, it looks better. However, because I'm recording a video, what I'm going to do is actually I'm going to step through it in a debugger. Okay, so I set a breakpoint on this line here, and I'm going to run it in a debugger. Okay, so it it stops, well, it kind of suspended at this line. It hasn't executed this line yet. So let's step over this line. There's not much to see just yet, because again, when we invoke a function that is a generator, not much work is done other than some preparation work done by Python itself. Okay, so if we look at the console, nothing here yet. Oh, one thing I want to point out is, yeah, FIPS is the generator that is returned by invoking this function, right? So we see FIPS is a generator. Now, next, literally, and that we are going to do next on the generator. And I'm going to show you what happened by stepping into the inner working of this call. So what next does is it's going to actually run the code that is inside this generator now. So that's why we are here. The debugger that brings us here. And if we, well, let's look at the console. If we actually step into, it doesn't matter here because print is a built-in. So let's say we step into it, it prints out this message on the console, right? FIP gen 100 is executing, and we can keep stepping through it. Python internally, and then initialize these variables, etc., etc. Check this condition here, and then it's going to print this message out right before yielding n, which is 0, the first Fibonacci number. Now we are ready to execute the yield n or yield 0 here. So what yield does is it does actually two things. One is it's going to return 0, it return n. So from the function. Okay, so in one way it works kind of like a function return. At the same time, because it's a return, the execution is going to go back to the caller. The control of the program is going to go back to the caller. It's not going to continue after this line. Okay, so let's do that. Step into, and voila, we are back. Well, in the next line, because remember what we executed just now was the first next, right? And it will yield 0, which is what's get assigned to result. And then this line is done. This line is done. We're going to go into the next call, the following next call. So let's look at what happens when we step into again. All right. Remember, we were here. We use 0. So the second next call, what's make this so remarkable is it picks up right where the previous next call ended, which is right after this yield 0. So we're going to continue. We still have n 0. It remembers what happened previously, and then we can keep executing, keep going. We're going to be back in the while the condition check, and we're going to print this n again, which is now 1, right? So we see that. So now we're back in U again, and I hope you know what's going to happen next by now, right? It's going to return n or 1, and then it's going to get out of this generator, but save the place so that if there is another next call, it's going to pick up right after it. So let's see, step into, well, we're done with the second next call, and that's why we come to this the following line, which in this case, I just have a line there so that you see we stop here. If we execute this line, then we are all done and the debugger has finished. So what we just saw in the debugger is basically what these 3 slides are trying to show. When we execute the next, we actually execute the code until we get to yield, and then the following next is going to pick up where we left off and then stop in at yield again. Now, using next shows us the inner working of a generator. However, we did say that usually when it comes to a generator, we just put it in the for loop, right? Now, in that case, then whether a function is written as a traditional function, in this case, right? Fib list 100 just return all the Fibonacci, the first 100 Fibonacci numbers, and then the generator, when we want to use it in a for loop, the usage is exactly the same as a non-generator function. So why bother with the generator? Well, there are several reasons. The most important one, in my mind at least, is the memory usage. And let me explain what I mean by that. So here I use a built-in method from the syst module that it's called getSizeOf, and unsurprisingly, it gives us the size of the object that we pass to it as its argument. So in this case, I'm going to get the size of the result of fib list and fib 1000. I'm going to do the same thing for the generator. Okay, so let me run this and look at the result. So let's look at the first two lines. So fib list 100 and 1000. The size for the first list of the first 100 Fibonacci numbers is 900 or so bytes, and for the first 1000 is 9000 bytes. So unsurprisingly, it's about 10 times bigger, right? So because here is a list of 1,000 numbers, and here is the list of 100 numbers. All right, now if we look at the size difference, or the lack of difference between the generator, generator 100, the size is 112, generator FibGen 1000, the size is remarkably the same. And now when you think about it a little more, how generator works, it should not be such a big surprise, right? Because, okay, when we run a function that is not a generator, a traditional function that returns all of the result, well, it has to do everything, right, when it was invoked. And in this case, it computes however many number of Fibonacci's it has to compute, and it has to store all of them, right? It cannot throw away anything. So it both takes up a lot of time because it has to do all the work up front, as well as to store all the results. So it's going to take up a lot of space. And as we saw, the space that it needs grows with the size of the input problem. On the other hand, when a generator is invoked, well, we saw that there's very little work that's done. Python does a bit of preparation, but that kind of preparation work, it is constant regardless of the size of the input, because again, it really hasn't done anything yet. And that's why in either case, the memory usage of the object that represents the generator is exactly the same. Now, sure, the generator, when we execute it, like by calling next on it or in a for loop, it will do the actual work. In the process of doing actual work, it may allocate memory as it needs to. Think about it. In this case, the Fibonacci generator, it has to compute the next one Fibonacci number, right? So in order to store that one number or maybe a couple temporary variables, it's not a whole lot of memory that it needs. Now, I'm glossing over some technical details here, but the important lesson is that generator, when used properly in the proper problem, it can save a lot of memory. So the question is, when do we use generator? Well, given what we just said, one scenario is if we have only limited amount of memory, and we almost always have limited amount of memory, right? Memory is never infinite. So that's a good case to use generator, or if we simply don't want to waste memory, even if we have a ton of memory. Okay, so another reason is that given that generator does the actual work as necessary, so it doesn't do everything up front, So it's very good if we might, in the course of going through our work, we might only need some of the partial results. So in this case, instead of, generating 1,000 Fibonacci number upfront and then figure out later, we might only need, 10 of them, then we should just generate these Fibonacci's as we need them. And that generator is also very good for that. And we will see other examples of using generator as we go through the rest of the class.